Hello, I'm JW. Today we're going to have a look at this thing behind me, which is a demonstration of diverted neutral current. Now, important thing about this is it uses 12 volts AC. This means it's perfectly safe to actually use and poke about with and do things you wouldn't normally be able to do if it was 230. It's also an isolated supply, so improving the safety further. So just bear that in mind when we look at some of the demonstrations shortly, in that you would not do some of these things if it was an actual 230 volt supply or if it was a real set of installations. Now what this represents is two houses, basically one on each side there, both identical and both connected to a TNCS type of installation. This is where you have a single combined neutral and earth conductor coming in, and of course the line conductor as well. For loads in this installation, each property has two lights. They're the ones you can see at the top here, 50 watts each, and those one are 12 volts as we already covered, so it's going to be around 4 amps or so for each one, circa 16 amps in total. And we've got the usual other parts here, which we'll now have a look at in a bit more detail. Now both sides of this are identical, representing two individual properties, and let's have a look at this side just to cover what we've got. So our incoming supply here, this is a CNE cable or combined neutral and earth cable. So we've got our line conductor going over this side and then our combined neutral and earth over here. Now normally there is a cover over the bottom of this so you can't actually see this split. We've left that off here so you can obviously see what's going on. Line and neutral conductors coming off to our consumer unit, and our earthing conductor here also comes off the same connection as the neutral, goes to our main earth terminal. In this case it's outside of the consumer unit, so we've got our earthing conductor then going over to the consumer unit there, and our bonding conductor going over to our metal pipe here. This could be gas or water or whatever else, doesn't particularly matter, the point is it's metal, goes outside into the ground where we can't see it. Now because this is just a demonstration, we can actually remove the fuse here. Normally of course you wouldn't be doing this, this cord is just so it doesn't fall on the floor and break. So that's what a fuse carrier basically looks like, and it just bridges between the two of these, this being marked red because of course normally that would be at 230 volts. In this case of course it isn't. And then we can see inside here, this is just a solid block. So the neutral and combined earth comes in here, and then it's just split here to the neutral and then the earth, but it is the same metallic connection, so there's only basically the 2 points here, even though we're splitting off here, and that's why it's TNCS, C for combined here, and then S for separate within the installation. Now inside the consumer unit we have just a main switch here, and we have two circuits which are for these lights. So if we turn those on, and we can see that both lights obviously illuminate. This is basically its normal operation, so exactly what you would expect. Let's turn those off because they get extremely hot. And this side is exactly the same, it's just another identical copy of that. Same incoming supply, same light, same cutout, pretty much the same everything. This bit here is just the mains input cable, so that's not concerned with what we're doing here. Now the only other thing here is what's in the middle, which is marked up as earth electrode, and essentially that's what that is. It's equivalent to going outside in the garden, shoving a temporary electrode in the lawn, and then connecting a lead to that, so you can determine the voltage between the true earth outside and whatever metallic parts we have got inside, because bearing in mind if a fault occurs on the supply, then it may be the case that the earth terminal and other things inside are not at the same voltage as what's outside. And this is something you can actually do in a real installation. Just say stick a temporary electrode outside as far away from any electrical and metal parts as possible, and then just check the voltage between what's really outside in the true earth and then any metal parts inside. Of course in normal operation there won't be any voltage really between those two, but this is something that you could do. We've got it here so that we can use our voltage indicator. This is a 12 volt AC one only. It has a red light and a buzzer there. And we've got our two leads here. Of course one will connect to our effectively earth electrode outside, and then the other one we can just check the voltage on the other parts. Also bearing in mind that if this is showing a voltage of 12, in the real installation that could be a voltage of 230 or even more. Now the other tool here we've got is this clamp meter. This just shows the current in a particular conductor, just showing 0 obviously at the moment. I've done a video on these separately, so I'm not going to cover that in any detail. And it's just a question of clipping it around the appropriate conductor. and then that will show if there's any current in the conductor. Now, for the purpose of this kind of test, any clamp meter will do the job as long as it can do AC current, which is basically what they're actually for. You don't have to get some high expensive piece. Any kind of clamp meter will do the job. I'm going to use this little orange one in this case. Now, first of all, have a look at normal operation. So this is where our incoming conductors are absolutely fine, and our bonding conductors are actually just connected to the pipes in the side of the property, so they're not going outside. It say would be a plastic, say water supply coming in, converts to copper once it's in the property. So it's all a self-contained situation there. So if we go to our consumer unit here, and we can just turn on our two circuits, and then we can see there our lights are on, so all perfectly fine and normal. And we can check the current on our conductors. So starting with 0 there. So if we just clip on to the conductor here, we can see that got just under 9 amps there, or 8.9 amps going through our line conductor. And we just check on the neutral. And again, similar thing there, just under 9 amps there, 9 or so amps as well. So nothing unusual there. And if we check on our conductors here, our earthing terminal conductor there, or earth to the consumer unit, nothing. And on our bonding, again, nothing either, and even around the pipe itself, absolutely nothing. So that is a case of normal operation, exactly what you'd expect in pretty much any installation. Now let's see what happens if the incoming CNE conductor, which would be the one here, is broken. This will be happening outside in the street, where you wouldn't be able to see it. In this case, we just use our switch here. So, conductor's now broken. As we can see, the lights are no longer working, so whoever's in this property would have identified that there's obviously something wrong. Now, what about voltages in this particular case? Because bearing in mind we've broken the circuit basically at this point, or just somewhere near there. So we use our voltage indicator here, in this case connected to our earth electrode, see what kind of voltages we have. So this could be a useful thing to do, just stick a temporary electrode in the lawn outside, attach it to a flying lead there just coming into the property, and then check the voltages between that and the inside. So let's see what we have on our main earth terminal. So as you can see, this is now at 12 volts, and in a real installation that could be at 230, or in some cases even more. Anybody who touches that will get a shock. And what about our metallic pipe? Yeah, it's the same problem. So now all of the parts in our installation are now live. And of course, if we switch on or reconnect the CNE conductor outside, again, lights are back on, all working fine. And we've checked the voltage again. Well, yep, there's absolutely nothing there because it's all connected now back to the neutral of the incoming supply properly. Basically goes back to the same potential as the earth outside. Now we'll look at the situation where our bonding conductor and our actual pipe here does go outside as metal or steel, copper, whatever, and it goes outside into the street, and it's basically connected to the same pipe in the neighbouring property. So it's all linked through together, and this is pretty much what you get if it was a, say, a metal service coming into the property from outside. So we link those two together, so basically this one here and then the one over on this side are now linked together. So again, we'll just turn on our circuits in our property here, and as you can see, all working absolutely fine. So what about the current in our conductors? So let's check on our line conductor here. You can see there about that 9 amps we had previously. And we'll check on our neutral. Yeah, again, it's the 9 amps or so. It does say very bit where the clamp is positioned. But let's check on our earthing conductor here. We've now got just under 3 amps going through this. This is the one that goes to the consumer unit, so nothing there. What about our bonding conductor? Yeah, we've got about 3 amps going here. And if we actually check on the pipe itself, yeah, we've now got about 2.5 or say 3 amps or so going through our pipe. Now you might wonder what's happening here, but this is again normal operation. So although there's current on that bonding conductor, this is what you would expect, because what's happening, because it's linked at this point here, and we've now got this pipe connected basically to the ground or earth through outside, what's happening is some of the current is going via the conductor here. the combined neutral and earth, but because this is connected, we've got current going from here into our main earth terminal, through our bonding conductor, into this pipe, and then hidden underground, it's going through the pipe here, coming back into the property next door, through their bonding conductor into the earth terminal here, and going back through their CNE conductor just here. This is inevitable because, of course, that's a parallel path, so some of the current is going to go there. And if we were to go to next door and just check on their bonding conductor, we can see 3 amps there. And again on their gas pipe, yep, 3 amps there as well. And that's actually going through here, out into the thing there. And of course this installation's all totally turned off, there's nothing there, so if we were to check on their system, yep, just 0 on the conductors, yep, absolutely nothing there. Now it's important to realise this is normal operation, so you will find current on bonding conductors to gas, water or any other metallic parts quite often, just for the fact that there's parallel paths connected, because you've got both pipes connected in both properties, they're both connected to the incoming earth terminal there, and both back to that CNE conductor, so it's inevitable that any current will flow between the various parts in various proportions. It all depends on the resistance of various components and so on. But again, this is pretty much normal operation. However, what happens now if the CNE conductor on our property here is broken? And now we saw previously that when it was broken, all the stuff stops working and we get dangerous voltages on the exposed part. So let's turn that off and see what happens. Okay, well, nothing appears to have happened. Lights are still working, so nobody living here would be any the wiser if anything was wrong. Now, what about the voltages on exposed parts? So what about the voltages on our terminal here? Well, not really seeing anything. On the pipes, maybe? Nope, nothing there. What about on the consumer unit? Nope, nothing there either. So if you were to go to this property in this state, everything looks normal. You wouldn't even know that there was a problem. You could say all working, no dangerous voltages found, all seems fine. However, let's check those currents on our various conductors. So again, we'll go in on our line conductor here, and as before, it's sort of 8.9 or just under 9 amps we've seen before. And what about the neutral? Well, again, it's the 8.9 amps or so that we've seen before. Nothing to the consumer unit one because that's just from circuits within the property. What about our earthing conductor here? Well, as you can see, 8.9 amps. So what we've got here is the whole load current for this installation is going through this conductor. You notice it's 8.9 amps there. And if we go back to our, say, line there, yep, it's that sort of 9 amps or so previously there. And if we check on our bonding conductor here, yep, it's the 8.9 amps, and actually around our pipe, it's the 8.9 amps. So what's happening here is that because this is broken, all of the current that's coming back on the neutral here is going via this conductor into our earth terminal, via the bonding, into the pipe, and it's actually ending up next door over there. Now that installation's not even turned on, and again nobody there would know any difference, but if we check on their bonding conductor, you can see, yep, there's that 8.9, 9 amps again. So all of the current from next door is now coming through here, going through their piece here, and going into the bottom here, which is their CNE conductor. Now there's no dangerous voltages here because again all this is connected back to the neutral via next door, so nothing particularly going wrong there. And again there won't be any voltages here either for the same reason. Again, it's all connected together, part of the same system. And if we return on properties supplies here, again that all works just fine. So nobody would know that anything was wrong here because everything is working just as it should be. Absolutely no problem at all. Now in this simple situation where all of our current is going via our bonding conductor, so basically they all match up, the giveaway that there's a problem is that if we turn off our lighting, we can see that the load will drop and basically go back to 0. So that would indicate that there is definitely a problem here. But bearing in mind this is a very simple situation, and if it was the case that the property next door was on, we would also get some current here anyhow, so that's not particularly conclusive. Now what if someone was to disconnect this bonding conductor? What if it was not an electrician who knew you had to turn off the supply first? What if it was some gas person or something else just came along and just decided to undo it, because after all it's all connected to Earth and all that and so on? Well, let's find out. Well, as you can see, straight away we don't have any lights anymore, and if we try to put this back in, we can see that that is basically the conductor for our installation. More importantly, if we to take this out and just leave it, what's happened to the end of this? Well, this is perfectly safe. What about our main Earth terminal? So the act of removing this has made all of this live. Basically, in this case, it would be 230. So it's only 12 here because this is obviously a demonstration. And as you can see, put it back in. There's no voltage there. Now, of course, that situation is bad enough, but of course, normally you wouldn't be doing that. You'd be turning off the power first before you disconnected any conductors. But what's going on in the property next door here? Well, no power's on here, as we can see in our consumer unit. All turned off there. We can in fact turn off our main switch as well. So in the past, when no one bothered to check current, you might think, oh, it's now perfectly safe just to disconnect our bonding conductors, earthing, who knows what else, because we've disconnected the supply, we know it's not working, we've checked there's no voltages here, absolutely fine, and let's just remove it and see what happens. Now, if you were working in this property, you wouldn't have noticed that the things next door have just gone off, because of course that's in a separate property, you can't see it. But what we've basically done is broken the circuit for the property over there, because their incoming CNE conductor is of course broken, and now it's all going via this. So if we put it back in, yeah, it comes back on, and we can see that there's quite a bit of sparking going on here. So if you were a gas engineer and you just disconnected this, a bit of an old spark there could ignite some gas that just leaked out somewhere, cause an explosion. And what about voltages on these parts? Well, they were perfectly safe. What about our main earthing terminal? Yeah, nothing wrong with that. What about our consumer unit? Yeah, no danger here. What about the wire we just disconnected? And even worse, what about the pipe coming in from outside? So although this was safe, and we made sure that the system was off, and then we just disconnected it, we've now made it extremely dangerous. Live parts here, live parts here, and of course if this was connected to other things in the house, like taps or boilers or whatever else, well, guess what? They're all live as well. Stick it back in, so of course next door is now working normally. Check the voltage again. Yeah, nothing. 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 So the dangerous voltage only exists once you've disconnected that conductor. So what's the answer then? Because say we don't know of any problems here. Well, the answer is, before disconnecting any of this stuff, use clamp meter to see what is actually going on here. So bearing in mind we're still off here, nothing's working here, all particularly off power there. We can just check on our conductors for installation. Yeah, nothing there, of course. And we'll just check on the other one. Yeah, again, nothing there. That's our earth from our consumer unit. Again, nothing there, because that would be coming from the circuits within this property. Check on our bonding conductor. 9 amps coming in now. That certainly isn't something you want to see. So if you do see current on a bonding conductor, certainly if it's any kind of large amount like that, say 9 amps or something, there may well be a problem somewhere within this system. We can also see that same current on the pipe here. So again, there's that 8.9, 9 amps or whatever, and we can see that it's actually going through here into the cutout here, and then via the combined neutral and earth conductor we've got here. Now, as we saw there, if you find current on a bonding conductor, you probably don't want to be disconnecting it because it could be providing the connection for something next door or across the street or who knows where. And bearing in mind, if you had a whole row of properties where the CNE had been broken, you could end up with, say, 10 properties, all current, all going through one of the bonding conductors. That could add up to a very substantial amount. However, the problem is that the presence of current on the bonding conductors here, or on a pipe or whatever, does not in itself mean that there's a problem. It could be normal use. So let's have a look at normal operation, where we've got our metallic pipes here going to the other property over here, but also where it's going down the street to 3 or 4 properties over there, and also up the road here to another couple of dozen up there. So a metal water main through the street there, all metal pipes going to the properties, all bonded, all with TNCS supplies. So we'll start then just turning on a light in our property. We'll just do one in there, and I think we'll just do a one in here as well. So as you can see there, we have one light in each of our properties. Now let's just have a quick look at the current on various parts of this system. So in property number 1, we can just quickly check here on our conductors here. So about 4.5 amps there, that's on the neutral, and the line, yeah, 4.5 amps, pretty much what you'd expect. What's going on our terminal here? Well, that's one to the consumer unit, so nothing there. That will be representing leakage from circuits in the property, so 0 for that. And what about our bonding conductor? We've got about 2.2 amps there. And if we check on the pipe itself, yeah, we can see that 2.2 amps is there. So no faults here, but we've got 2 amps or something going through that. Now let's have a look in the property next door. Again, similar load is turned on, so we should see similar figures. So 4.5 amps or so on the line. The neutral is 4.5 amps. Again, there'll be nothing on the consumer unit because that's just from individual circuits. And our bonding conductor, it's around 2.2, 2.1, and we can see that on the pipe itself. So 2.1 there. Now what would happen if we turn on additional load in this property? So let's turn on an extra light. What's happened to our conductor current on our pipe? Well, now it's actually up to around 5 amps. What about the pipe next door in the adjacent property? That's now gone down to 1.5. And we'll check on our conductor here, yeah, 1.5. So the situation now is that this current is now disappearing in multiple different directions. So our total load on our installation in this particular property is just under 9 amps, 8.99 or something. So say 9 amps is there. If we check right here on the conductor, we can see roughly 5 amps is going through there. But what's going on in the next door property over here? Well, only one light on in here, of course, and we've seen that previously. What's going on the main conductor here? 1.5 amps is going through there. 1.5 there. And again, we check on our supply here, it's about 4.5. So on the left here, we've got 4.5 amps of load, 1.5 or so going through those bonding conductors. Over here, we've got considerably more load, say about 9 or so, and we've got about 5 amps going through the bonding conductors over there. Now, if these figures don't seem to add up, well, that's wholly the point. What's going on here is that some of the current from this installation is going via the CNE conductor here, and some of it is going through here, over into our pipe there, and some of it is going to go, say, to up the road to the properties that obviously don't exist. Some of it is going to come back here onto this one and go through here and back into the conductor here. Bearing in mind, they've also got a different load current here going into this, and some is here, and some is here, and some is there, and some of this is going along the street to the properties over there, which currently don't exist. So we've now got current going in multiple different directions. So the actual magnitude or the measurement of the current we're seeing here really doesn't tell us anything other than the fact we've got some current present, 1.5 on this side, and nearly 5 over there. So if you were working in this property, I think, oh, we'll just turn off the circuits so we can disconnect the conductors. Do we have current here? Yeah, we've now got 0.7. What have we got over here? 2.9. So see, it's all changed, but it hasn't necessarily changed in a way which is particularly obvious. Still getting current there, a fairly small amount. Getting a fair amount of current here, quite a large amount in this particular case. And we can just turn on an extra load here. What have we got now? 5.7. And in the property with nothing on, 1.2. And if we just leave it there, the 5.8 is there. If some bonding up the street was disconnected in a property which has nothing to do with this one, the current here can drop to say 3.4. And it might come back, say, to 5.7 again. It could also go down to, say, 4.8. 5.5. 5.62. So it's completely unpredictable. Now, as we saw there, the current in the bonding conductors is going to be there in normal operation. It's pretty much inevitable, especially when you have a whole row of properties all connected to a common metallic part. That could be, say, a gas pipe like we've got here, or it could be a water pipe, or it could even be a metal framed building like one of those industrial warehouse things divided up into, say, 6 units. The metal frame is going to be bonded, and of course current is going to circulate all over the place depending on various loads being switched on and off in various different parts of each property. So unfortunately the presence of current on these does not necessarily mean that there's a fault, and in fact most of the time there won't be a fault. It's just inevitable that you've got all these parallel paths for current to flow and circulate around in various different directions. But of course if there is a fault, it can mean that when you disconnect here you get a dangerous voltage. So the only real advice can be given here is, first of all, check if there's any current here first before disconnecting anything. If there isn't anything there, well, again, that's fine. But if there is, and you do need to disconnect this, when you've disconnected it, check at the end of here to see if there is any dangerous voltage present. Because if there is, you've basically just disconnected basically return neutral conductor for another property or properties. And that's where you'll get, say, 230 volts or possibly even more on the end of a wire you've disconnected, or possibly the actual terminal itself, depending on exactly where the problem was. Now that is it for this particular video. Bearing in mind what we've shown here is already getting fairly complex, but this is not even the start of it, because we're only dealing with single phase here. And as I've sort of hinted at throughout the video, there are circumstances where this can actually be more than 230, and in some cases up to over 400 volts. Particularly where you have properties that are supplied with a single phase each, but each property is supplied from a different phase in the street. And we're going to look at that in a future video. But until then, thanks for watching.